All right, so hello everyone. Welcome back to the third session for these full series of video um, mentoring videos. And in this session three, what we hope to do is going to be a more realistic problem. And I do hope to spend a little bit more time talking about the construction and some of the coding languages regarding the class. How do we set it up? And the functions or the method within the class. And also finally, just spend a little more time talking about the nonlinear solvers, so Newton-Raphson method, which is the one we're going to be using for this particular section. So let's get started. The figure on the left shows you the basically the structure we're trying to model in this case. So if you are from civil engineering, this should be very familiar. If you're from mechanical engineering, maybe at some point you've seen something like these, but overall it's not too complicated. So each truss they are able to take either axial load or tension. They can take axial load is going to be either compression or in tension. And for each of the node, these forces needs to be in equilibrium. So if you sum the vectorized load about each of the node, you should get zero at the end of the day. So that's truss. And we want to make things a little bit more realistic by assigning the systems, say the cross sections and also the Young's modulus, the material properties. So each of the span in this particular truss, it's assumed to be 1 meter, and the cross section is 1 centimeter by 1 centimeter with a 2 gigapascal Young's modulus. So this is actually a very, very soft truss, and we created that for a reason because we do want to see large deformation um, at the end of the day. So that's one of the reason. I deliberately make it very small, and apparently with the design like these, you don't want to stand on top of it. It's most likely very unsafe. But anyway, we're not gonna consider the buckling of the trusses, which I believe some of the members in compressions with these size, they are really susceptible to buckling, but we're gonna neglect that just for simplicity. And the load is going to be applied at this node here at the center. That's going to be 1,000 Newton. Um, all right, so let's get started. We first want to initialize and define some of these terms. Let's say the height of the truss, 1 meter, length of each span, 1 meter. The bar area is 0.01 meter times 0.01 meters, and that will give us this value here. It's 1 centimeter by 1 centimeter. And then the Young's modulus is 2 to the power of 10 to the ninth. So I do recommend you to use international unit because oh man, if you're coding an empirical unit, you need to do the conversion yourself. And this conversion in the empirical unit, it's difficult. Don't do that. So, okay, use international unit. And the rest of the things are just like what we've done. We define the node, we define the bar element, create that object, and then the assembly class is actually simpler than what we have in the section two. So we only have um, two classes within these assemblies. So there's going to be a node and there's going to be a bar. We don't need that active bar here, right? If we go back to the section two. In that example, we have node, bars, and active bar. So here it's just a simple truss, so we no longer have that active bar in it. So if you go into that assembly class truss file, what we have is double click it. Oops, sorry, this is still section two. We need to go back to section three. This is the section three's assembly truss. And on the right, so it has only node and bar. That's the property of this class. So nodes and the bars. So if we go to the section two, um, then the assembly class for section two is this one. You can see that it has an additional active bar elements there. So, in addition to talking about this, I do hope to just spend a little bit more time talking about the solve, force, and stiffness matrix function here. So, these particular function is where so basically we use these functions to find the global force vector and also the global stiffness matrix and send that into the nonlinear solver. So that's the main way these assembly class talk to the nonlinear solver. So the nonlinear solver will take these forces from here and do the incremental and iterative calculation to find the equilibrium path. So if we stare at these, this is from the section 2, where there is an active bar, and compare that with the solve fk function in the in this section 3 without the active bar, you can see that basically what's going on is that on this section 3, there's no forces coming out of active bar because we don't have that element, right? That makes sense. So what this function is doing is basically for each type of the element, you solve their force and stiffness. So force vector and stiffness matrix, and it sums them to get a resulting total global force and global matrix. So in this situation where we only have one element, this is just one indexes. So that's something if you want to like cook up your own assembly, you need to know how to do using these codes. So I would encourage you as we keep moving, we will see a lot of more examples. And in those examples, there's going to be different element being used. And we will look into this different solve-fk function and also the assembly class definition and hope that you can spend some time reading those and that will allows you to use the code for your own own research to create the system that you want, right? So if you go into the source code, right, there's actually a lot of elements for you to choose from. So you are able to cook up your own assembly class for the problem you're looking at, and then when you do that, you will want to go into these assembly class and modify the terms here and there. So okay, so that's one of the things I do hope to explain. But while you're just reading this, it will take some time for you to understand it. So if you feel lost here and there, my suggestions for you is actually to keep going forward, and after you have worked on multiple examples, you typically will have a better understanding of what's going on. So it does take some time. If you've never done this object-oriented programming, it does take some time to understand the way these codes are typically organized. But the way this is organized is really similar to any sort of a conventional or commercial finite element or simulation code. Um, they pretty much follow the exact same um, organization with the different languages, of course. All right, so that's what I hope to talk about here. So inside of this assembly class, this we just briefly discussed, right? So for the solve fk of this assembly class, because we just have one bar element, we just find that forces and stiffness from the bar and return the forces and stiffness from the bar. And that's all we need for the nonlinear solvers to operate. So keep moving. This part is just to define the nodal coordinates for a structure like these. This is actually a very simple process, right? So this is the 1 to 5. That's the first line of the trusses at the bottom. And this is the second line of nodes at the top. And after that, we can actually try to run it. Okay, so in order to run it, let's go back here, add the source code to path. That will allows us to run these and get the current folder in these folders so that we know where to look for these assembly truss class. I've added her. And let's try to plot the node number, and let's get a stop here, pause it here. So the code should run without problem. So when you're plotting these display range variable in the properties for the plot class is how you can organize or change your basically the ranges you want to plot. So for instance, I want to plot from 1 to 5 because from -1 to 5 for my x-axis. That's why it's -1, 5. And I will want to plot from -1 to 2 for my z-axis. That's what's done there. And this thing for the y, it's from -1 to 1. That's perpendicular to this screen. And then of course we can change the view angle. So 0, 0 will give you XZ plane by default. But if we change them and rerun the code, you can see that we can change where we look at these 5 nodes. So 30, 30 will give you a view angle that's slightly upward and then slightly rotated to the right. All right, let's change to 0, 0. It's probably the best angle because we're working in a planar problem in the XOZ plane. So looking good. And we need to define the bars, right? That's something we've already done in the section 2. So the first 8 groups of bars are the top and the bottom line of truss. So that's 1, 2, 2, 3, 3, 4, 4, 5, right? That's exactly what's shown here. Top line 6 to 10. And then the second one is the vertical trusses. So connecting the node in the vertical direction. And then these are the diagonal bars. So we just define the connectivity according to basically these figure at the top, and that will done. That will have the job done. And then we find the total number of bars we've defined and set up the area and the Young's modulus. So we assume that all the bars there are the same. And this is how we set it up, the area vector and also the Young's modulus vectors. If you want to make change to like a single bar, we'll just change, find an index and change it. I will show you that later as a practice. But then after that, what we can do is just plot it. So let's do that before starting to set up the load. Okay, all right, looking good, right? So we have the system plotted. It's just like what we're looking for in the problem statement. So the next thing I would like to spend a little more time talking about is to set up the load and just get an overall understanding of the Newton-Raphson. So what we're doing here is this is Newton-Raphson solver, so solver Newton-Raphson loading. And there's going to be a following section later with a dedicated full section just to introduce you to what the Newton-Raphson algorithm is doing. But right now, let me just give you a very brief introduction. So basically, the Newton-Raphson will break up your load into multiple steps. In this case, it's going to be 10 steps. And within each steps, it adds the load and they run a Newton step to iteratively find the new equilibrium position and then update the deformation of the structure. So after that, it goes on to do the next steps. So for instance, our goal here is to load the entire load at this node and apply a 10,000 like a 1,000 Newton force at this particular node, right? So what this code is currently doing is applying 100 Newton load. So by the way, this is all in international unit because if you use the standard international unit, you don't need to. You can drop everything. You don't need to do any conversion and your result will be right. That's the one big advantage of using international compared to the empirical in the United States. But anyway, so this is at node 3, right? So this is node 3. That's exactly where we want to load the structure. We break that 1,000 Newton into 100 Newton step. And the total increment is 10 steps, right? So if we keep adding 100 Newton for 10 steps, we end up having 1,000 Newton that's pointing downward. So this is what's being done here. And within each increment, the algorithm is allowed to use 30 steps of Newton iteration to find the equilibrium. So basically solve for the extremum in the potential function. And if you really want to get into the math part of it, but that's just something that's being done here to find. So basically find a deformed configuration that gives you equilibrium. That's how you can understand it. And after it found it, we just tell the Newton-Raphson class to solve the result. And these will give us a history. That's the deformation history. So U his, it's a deformation history. And we finally plot the deformed shape of the system, and we are only plotting U his. It's a step. So this first index is a step, and every other. So this is the node number, and this is 1, 2, 3 for the XYZ deformation. So that's the structure of the U his, and we're just plotting the final shape. So let's see what we got here, right? There we are. So as you can see, our trusses got deformed downwards a little bit, and you can actually see the difference between this deformed shape, which is in black, and that gray shadow, which is a little bit behind it. So I do make this truss extremely soft just to allow people to see these deformation. So this is actually the output from the solver. So R is the residual, so how far you are away from the equilibrium. It's a norm of the global force difference in the force. And you can see it start with the first increment. Oops, excuse me. Increment 1, 2, 3, 4, 5, right? It's basically incrementally increasing the applied load from 0 to 1,000 Newton, and we specify that every incremental load is 100 Newton. So that's how we achieve it in 10 steps. And then for each of the steps, we do just 2 to 3 iteration to find the equilibrium position, and because we aren't pushing it very hard, so that actually helps. So what we can do here is let's try to see if we make one of the bars to be like much softer. So for instance, let's pick a bar here. Um, how about picking this bar here and make it to be very soft, right? So I don't know if you play Polybridges or not. I really love playing Polybridge. It's a very fun game. And you know, in Polybridge, there's this spring element that you can use to bounce your car, and that spring is very soft. So let's try to make this bar here very soft. And let's see what's the number of that bar. Okay, 17. All right. So what we can do to make that bar soft is bar E vector 17th. Make it to be 100 times softer than what it used to be. Right? Let's do that. Divided by 100. So that will make that bar really soft. And let's hope that our algorithms too can converge. Oh yeah, it did. So there we are. So after making this bar very soft, you can see that this outer truss here will no longer be able to stay in the more rectangular shape. These trusses get compressed a lot, and then there's a much larger deformation that's happening here. So anyway, going back to here, there's a couple more lines here that we are doing. So the final few lines are just to find the strain of each of the bar elements. and then compute the strain, compute internal forces of each of the bar. So basically, because we're using a linear elastic bar element, so the forces of each bar is the strain times the Young's modulus times the cross-section area of that bars. So we're assuming that even under some of the larger deformation, the cross-section, we neglect the shrinking or expanding of the cross-section. Here, if the deformation is small, that's usually a good enough assumption that we make. So dot times. So these particular, it means it will times this vector per element. So the first element from E vector will be used to multiply the first element in the A vector. That's what dot multiply means. All right. And in the plots, there is also this plot bar force function that's already there. And you can see that due to the large deformation and because this bar is very soft, um, the forces is very different from what we would expect with the linear solution. And let's get that soft link away and recompute the result to see what we've got here. All right, so this is more of a standard solution you might be able to find using that's going to be closer to the linear solution that you find in if you use, say, structure analysis class, the analytical method you can use to solve for the trusses. And for these from these sections, I will be leaving some of the practice problems for you to, just to play around and to see if you can practice what you've learned from here and use the code to get the answers. And the first one is actually to asking you to compare with the analytical solution and to try to see how close are they. And the analytical solutions are typically based on the linear result. It assumes infinitesimal deformation. But here, for this particular deformation we're seeing here, it's actually large enough to the point where you can see nonlinearity and nonlinear effect. So for instance, if you solve this particular system using infinitesimal linear analysis, this bottom line of bars most likely is going to be pure zero throughout. But because of these node is actually dragged downward, um, you can see it here. It actually developed a very small force, but overall it shouldn't be too different from the analytical solution. And the second problem is just asking you to change the code to 8-span and try to see if you are able to recreate these model, just like what we've done in the section 2, right? That's going to be a good way to familiarize with, make sure that you're familiar with these object-oriented programming type of way to code and also to get the solver to feed out the results that's reasonable for you. All right, so that's all I have for the section 3. And as always, have a great day.